Okay, we are in now video lecture 22, and having given you a brief description, a brief introduction into what's going on, we start with the actual phase diagram. Now, the total phase diagram of a CaO, MgO, SiO2, H2O system over the whole range of pressure temperature conditions, is very complex. You have many phases, many phase fields. So what happens? You essentially lose track of things. So what we do here is to introduce you to the essential concepts of it. We take a part of the system, somewhere between 450 and 650 degrees centigrades at low pressures, about 2 kilobar pressure, for the XH2O range from 0 to 1. So we have XH2O varying from 0 to 1. And remember, XCO2 varies in the opposite way. And the temperature range roughly 450 to 650 degrees centigrade. This is roughly crossing from, the green sheet phases is roughly at 500 degrees centigrade. It's roughly at 500 degrees centigrade, where the L2SiO5 triple point exists at that temperature, and a near vertical line. We will come to that later on. But that's the temperature range we're looking at. So essentially, if you take 450 to 650 degrees centigrade, and at 500 degrees centigrade you have the green sheet phases conditions, then you're looking at green sheet phases to amphibolite phases transition at quite a low pressure. We will look at that phase diagram, and then we will try to make our assumptions. But before we reach there, there is still a few things to do, and we will do that first. Now, in this part of the phase diagram, so we have the following phases which exists: SiO2, CaO, let me see if I have got this right, yes, CaO, MgO, plus SiO, plus CO2, plus H2. This is what we have. And the phases that are stable here are quartz, calcite, CaCO3, calcite. Then we have a 50:50 line here. So we have and a 50:50 line here. So this is where you have dolomite. So you have calcite and dolomite. And you remember this point, this is dioxide. And then somewhere down, if you divide it into 3, this is where you have phosphorites. So these are the phases, some more phrases: quartz, dolomite, phosphorite, yes. Another small phase that appears at around 50% is wollastonite. And then I will plot another point, and this point, for a particular reason, I will draw this join. This join is somewhere like this. And here you have something called tremolite. I will write down the formula for you: Ca2, Mg5, Si8, O22, OHO twice. I have not drawn other phases. Say, for example, anthophyllite, Mg7, Si8, O22, OHO twice, Mg7, Si8, so it will be close to 50-50. I have not drawn. And the tremolite plotting position is below this line, or towards the dolomite side of the diagram. Tremolite occurs here. Dolomite is here. This is calcite. This is dolomite. This is wollastonite. This is dioxide. This is phosphorite. This is quartz. And these are the phases that are stable in that range of 450 degrees centigrades and 650 degrees centigrades, roughly in that range. These are the mineral phases that are there. I have also ignored here for making things simple, because my philosophy is that let's make things simple first to get at the basic ideology. You can always complicate a thing, but the point is, let's understand the science of it. And when you make the complication, you're already aware of the science, so it doesn't matter. Another mineral that I have avoided plotting here, although it comes in this particular field, in fact, the papers that I've referred to, it's there. This is talc, TLC talc, which is Mg7, Si8, O22, OH4 twice. I have ignored this mineral at the moment. Makes my life simpler. But you can, once you have understood it without talc, in the PDF that I have sent you, talc is included. You can include talc and you can do whatever you like. But it's important that you understand the science of it. So here in this diagram, say for example, I will quickly go here. Say for example, let's say okay. Let's take a intersection. Say for example, quartz plus dolomite, and you have a tie line, calcite plus tremolite, right? So we write the expression here, CaMgCO3 full twice, that is what is dolomite. Then we take quartz plus SiO2, and then we have tremolite, which is Ca2 Mg5 Si8 O22 OH4 plus, right? And you have calcite, so plus CaCO3. If we take this reaction, for example, and we try to balance it, you will see this magnesium occurs only between these phases, tremolite and dolomite. So if you have 5 magnesium, then we can write 5 here. And so you have balanced magnesium. And you have 5 calcium here. So out of which there are 2 calcium here. So this becomes 3 calcium. So you have balanced calcium and magnesium. On the other hand, here you have 8 silicon, and there is no silicon here, so you can safely put in 8 SiO2. Right? So we have taken care of calcium, magnesium, and silicon. But we have still H2O. So we have H here, there is no hydrogen, so you write plus H2O. You see, hydrogen is balanced. And now, carbon. So you have 2 into 5, 10 carbon, and here you have 3 carbon. So you have to have 7 CO2 here. So that is the reaction. That is the reaction. In this reaction, dolomite, 5 dolomite moles react with 8 quartz moles, consumes H2O and produces tremolite and calcite with the liberation of carbon dioxide. So we have essentially 5 dolomite plus 8 quartz plus H2O is equal to tremolite plus 3 calcite plus 7 CO2. That's the reaction. So dolomite reacts with quartz but requires hydrogen. So hydrogen is consumed and CO2 is produced. And if you see, for 1 mole of H2O consumed, 7 moles of CO2 are added. So if you have a fluid in a closed system, so the reaction consumes the H2 of the fluid and liberates carbon dioxide, means it is making the fluid more carbonic. So essentially the reaction is a sink for H2O. It's a sink for H2O, but it liberates 7 CO2. Why is it a sink? Because this hydrogen is now trapped in the structure of tremolite. Is trapped in the structure of tremolite. So H2O does not exist as a fluid. It exists in the structure of the mineral. So this is a reaction where you have H2O sink and 7 CO2. So as the reaction moves this way, as you promote tremolite plus calcite, the fluid that is already there in the rock becomes more and more carbonic. Have you understood? Okay, I think we will do it later. We say, for example, so we keep this equation. I have a definite reason why I'm writing down a few equations, some of the selected equations. And then yesterday we wrote another equation that was, I forgot. Yes, yesterday we wrote a reaction, dolomite plus quartz is equal to dioxide plus carbon dioxide. So that means that reaction will be, if I now erase this, dolomite plus quartz once more, and you have dioxide on the green line here. So you have dolomite plus quartz producing dioxide. But there is no H2O in this situation. No H2O in this situation. But here H2O and CO2 is on one side H2O, the other side CO2. You could have reactions where CO2 is on this side, H2O is on that side. Now let me write another reaction. I will just erase this green line because I have to. Let me take another reaction. Okay, tremolite plus dolomite. So here, tremolite plus dolomite gives you forsterite plus calcite. Forsterite plus calcite. You see that? Tremolite plus dolomite is equal to forsterite plus calcite. So I have written this reaction. It is tremolite plus 11 dolomite. You please cross-check the coefficients when you are studying it. 8 forsterite plus 13 calcite plus H2O plus 9 CO2. So, you please cross-check the coefficients when you're doing it. This is tremolite plus dolomite. So it should be 11 dolomite plus tremolite gives you 8 forsterite plus 13 calcite. That's the reaction. And you have H2O and CO2 produced in the ratio. Here the ratio of H2O is to CO2 is equal to 1:9. H2O is to CO2 is equal to 1:9. In which means that you're reacting two minerals. Dolomite contains carbon dioxide. Tremolite contains hydroxyl ions, hydroxyl radicals. Dolomite contains carbon dioxide. They break down to produce this, and you liberate H2O and CO2. Now, on this reaction, I want to elaborate a little bit more. And this is the following. Now, you should remember this, it's important. Say, for example, I draw a red line. This is XH2O. So, XH2O, let's say XH2O is 1.0 here, and this is 0.0. That means XH2O increases this way, and if you take HCO2, then HCO2 of course increases this way, like that. So, this reaction is producing H2O is to 9 CO2, 1:9 ratio. So that means if you take this as 1.0, this is 0.5, 0.6, 0.7, 0.8, 0.9, 0.4, 0.3, 0.2, 0.1. So this is 0.1. 0.1, which one? XH. This will be XH2O 0.1. So XH2O, this is XH2O equal to 0.1. So what is happening is the fluid that is being produced by the reaction is here. This is the composition of H2O is to CO2. 1:9, which means this much is XH2O, this much is CO2 because CO2 is 1.0 here, and this much is XH2O. So this is the fluid composition that is being produced by this reaction. Make no mistake, this is being produced by this reaction. Now listen to me very carefully. When tremolite was reacting with dolomite, it is not that there were no fluids. There was a fluid. There was a fluid. You can't see it, but doesn't mean that there was no fluids. Because they came through some reaction. It's a closed system. It's not that they did not have fluids. Let's say that fluid that was there initially, where you had tremolite plus dolomite, forsterite calcite has not still formed, but you had tremolite plus dolomite. Let's say the fluid composition was 0.5. That means in that fluid, XH2O was 0.5, XCO2 was 0.5. That fluid. Which fluid? That fluid was in equilibrium with tremolite plus dolomite. Right? Now you see, you have this fluid, XH2O is equal to CO2 is equal to 0.5, and you produce XH2O, where XH2O is to CO2 is to 1:9. That means you are producing a very carbonaceous fluid, and this carbonaceous fluid is not going out, it's a closed system. So what this is doing is, it is driving this XH2 initial composition towards more CO2. Or in other words, it is making, this reaction is making the initial fluid composition under closed system condition more carbonic. It is drawing the initial fluid to more carbonic system because the XCO2 value of the fluid has a higher value than the XCO2 in the liquid. Have you understood? Now, if we go to the other end of the spectrum, let's say you had a fluid here. You had an initial fluid. This was one situation where your initial fluid XH2O is equal to CO2 is equal to 0.5. If you had an initial liquid here, or fluid here, that means what? say XCO2 was 0.95. XCO2 was 0.95. But you are producing a liquid with XCO2 is 0.9. So what is happening? You're reducing the carbon dioxide in the initial fluid. So the movement of this fluid is in this direction. Till this point. It can only be this and it can't go more. But if you were with the blue line here, then your fluid composition would have moved in this direction. Have you understood? If you started with a more aqueous fluid, XH2 0.5, and you were producing a fluid XCO2 0.9, then your initial fluid will move in this direction. This direction means your initial aqueous fluid will become more carbonic. But if your rock, same tremolite and dolomite, had an initial liquid in green, which means XCO2 was 0.95, but you are now adding XCO2 0.9. So what it is doing here, it is driving the initial fluid to a composition XCO2 is 0.9, which means it's hydrating a carbon, very carbon rich. It is adding more H2O to the carbon. Now you can understand one thing. The fluid, in case of closed system, if you're looking at the fluid composition, somehow we know we have determined XH2, XCO2, XCH4, etc. All this came through certain reaction systems, sequence of reaction. You only see the end product. So when you see that end product, don't think that throughout the evolution of the rock, you have that end product. In fact, you never had it. The composition, the inherited fluid composition of the rock must have been very, very different. Over reactions through time, your fluid composition is now what you have computed. So when we computed those XH2O, XCO2, XCH4, XO2, XH2O, all these things, remember it was referring to a particular equilibrium. How did you calculate those? Remember the input variables, so XMG, XFE, all these values. Those values are what? Those values are the end products. So based on that end product equilibrium, you are finding out the fluid composition for that equilibrium. But it does not mean that that fluid composition, even if it is a closed system, that was the fluid composition of the rock when it inherited it. No. Just like you, for example, what you are today and what I am today, you know, we all have our genetic codes. So that contributed. Also another thing contributed is the experiences that you gathered in your life, which is very short till now. Mine has gone way beyond. So over the time, the expertise that I have drawn, the DNA that I inherited, that has made me what I am today. And that is what is making you today and will take you to the future. And I'm sure many of the characteristics that have inherited now will never be when you reach my age or even older. I wish you all live 100 years. But it will not be the same. It is a cumulative effect of the inherited signatures and the signatures that you acquired over time. Same with metamorphic rocks. The one that you see now under the microscope is a sum total end product of many such processes that went on in the rock. And that is very crucial. There is a great similarity between metamorphism and human life. Except that, because there is a great similarity. So when you see a rock under the microscope with its minerals and its composition, don't think that that is what was there when it all started. It never was. And it will never be if you subject it to another set of conditions, even assuming that you're a closed system. Because the reactions change the fluid compositions. The reactions change the mineralogy of the rock. So what you see today is the sum total of those products that it acquired over time, passing through a pressure, temperature, fluid regime. So you see essentially the end product of it. You don't see it as this is what it inherited. No. You are today, or I am today. What we are is not what we inherited. We have modified ourselves based on our interactions with the society, our reading, our thought process, what we have tried to understand, your friends, your accompaniments, whatever you have done. It's a sum total of that. But you acquired certain things by virtue from your parents, from your lineages. You did acquire something. But what you're today is not a whole total of that. No, not at all. Right. So we have, I hope you have understood this, that if the rock inherited an aqueous fluid, and this was the experience that the rock was undertaking, 1:0.9, then the initial inherited composition would change in this direction. But if the inherited fluid composition was this, then the fluid composition would move in the opposite direction. We will go into this in more detail, but I think at every step I will tell you what it is. Otherwise it becomes very complicated to tell it all together, and then everything is lost. And again, as before, before we just conclude this part, we started with an assemblage tremolite dolomite, and then we reached the situation when this reaction was on. You had tremolite, dolomite, phosphorite, and calcite in certain ratio. This is what we had when the reaction was going on. And then, when would the reaction stop? Either way, from this you could have two sets of assemblages. One is, if tremolite is gone, dolomite, phosphorite, calcite, or you could have, if dolomite, the reactant was gone, tremolite, phosphorite, calcite. So, dolomite, phosphorite, calcite here, because tremolite could be exhausted, or you could have tremolite, phosphorite, calcite if dolomite was exhausted. What would determine it? The initial composition. The initial composition. We will go into this more detail, but you must understand that these two different assemblages does not really mean that, does not mean they fall at different pressure, temperature condition. It just means that it could be a fallout of the initial composition, of the rock that determined tremolite, how much tremolite and dolomite was there initially in the rock. That would determine what would be the assemblage that finally stabilizes. Right. Now, while we do this, we come to an important part here. Now, here, what you see here, it is important. You can see that you have dolomite plus quartz, solid phases reacting, fluid phase, and in your product you have solid phases and the fluid phases. So, I can sort of write it, I will take this actually. We can write a situation, a reaction, where we can write a reaction, A is equal to B plus MH2O plus NCO2. We can write a reaction. What is A? A are mineral phases. Tremolite, dolomite, calcite, quartz, whatever it is. What is B? The product minerals. A is the reactant minerals, B is the product minerals. And you have H2O and CO2. In this case, for example, m is greater than 1 and n is greater than 1. Or m is greater than 0, sorry. M is greater than 0, n is greater than 0 in this reaction. A is equal to B is equal to MH2O plus HCO2. Here, M is greater than 0, positive, and N is greater than 0. If it was like this, then say for example, M greater than 0, N equal to 0. What will happen? You will have a reaction, A is equal to B plus MH2O. Or you could have a reaction where M is equal to 0, N is greater than 0. What would this mean? It would mean A is equal to B plus NCO2. Or you could have M less than 0, N greater than 0. M less than 0. That means it is negative. If M is negative, then it should go on this side. So the reaction should be A plus MH2O is equal to B plus NCO. Have you understood? Because a reaction is never written with a negative sign. So M is less than 0 means this is negative. So this part goes on this side. So it's, and then it becomes positive. So A is equal to M plus H2O plus B is equal to A plus C. Or you can have M greater than 0, N less than 0. Now this would be, this N is less than 0, so you have N plus NCO2 is equal to B plus MH2. So if we can thermodynamically model this chem reaction, that is what I asked you to read out. If we can model this stem reaction, then we could change M and N and try to find out how the reaction slopes are and how the reaction slopes will. How the reaction slopes will happen. And what are the options left to us? Option is we have temperature, pressure, and another axis which is XH2O or XCO2. So, what we can do, either you can have a pressure temperature diagram where XCO2 is constant, or you can have PXCO2 diagram where T is constant, or you could have TXCO2 diagram where P is constant. So this is a pressure temperature diagram. We can examine this mineral in a pressure temperature diagram at a constant XCO2. That means constant XH2O also, because XH2O plus XCO2 equal to 1. Or you could examine this in a pressure temperature field PXCO2 at constant temperature. That means this is a pressure composition diagram where T is constant, isothermal condition. So essentially this is the plane, the PXCO2 plane. So essentially this is the plane that you're looking at, PXCO2. This is the plane that you're looking at. And the pressure temperature diagram is in this field. This is the pressure temperature diagram. You're looking at this field at a particular XCO2 value. Or you're looking at PXH2 or PXCO2 diagram where T is constant, or you're looking at a TXCO2 plane at constant pressure. So these are the three spaces that you can look for to find out how the reactions behave. Have you understood? So that is important point at the moment. The point is, if this reaction will be a function, as you can see, because all phases are pure phases, CONGSiO2H2O system, it's all pure phases. So the variables, metamorphic variables are pressure, temperature, XH2O or XCO2. So these are the three variables, pressure, temperature, XH2O or XCO2. And you can examine the reaction in a PT space, where XCO2 is constant, this plane, or you can have it at PXCO2, this plane. You can take innumerable sections with T constant, or you can take this TXCO2 plane, the basal plane, and intersect it at different pressure conditions. And you will be able to see the reactions. So remember, the reactions are a surface. So your reaction is a surface. This is also explained in the book chapter that I gave you to read in the last week. So what happens is, the reactions are essentially space. They have curved surfaces on PT, XH2, XCO2, XH2 or XCO2 space. So reactions are occupying a three-dimensional geometry. And you are cutting it. Say, for example, you have so it's something like this is a surface. So the reaction is essentially a surface. And you're cutting it with a PT plane, TXCO2 or TXCO2 plane. It will give you different intersections when you extend the plane and it cuts it off into different planes. So essentially, all these reactions that you're studying are essentially three-dimensional reactions. They occupy a three-dimensional space. Right? Okay. Now Now this was the reaction that you derived, that was derived and I asked you to read. So it is minus del SR for this reaction into del T plus P delta VR into dP plus RT into NXCO2 minus MXH2O dxCO2. This is equal to 0. This is the thermodynamics of that reaction, the derivation of which I gave it to you. Now see, if I want to find out dP by dt at XCO2, constant XCO2, what am I trying to find out? The slope of the reaction. Del P by del T is the slope of the reaction. At constant XCO2. So at constant XCO2, del XCO2 should be equal to 0. So essentially this becomes equal to 0. So this term vanishes. And so what we have essentially is, this is delta SR minus this is del SR my guy del VR. This is your very famous Clausius-Clapeyron equation. Clausius-Clapeyron equation. So dP by dt is equal to del SR by del VR. At constant XCO2, at dxCO2 is equal to 0. Now you see, you can also find out del T by del XCO2, and that is at constant P. Now you see what happens at constant P, del P is equal to 0. Constant P, del P is equal to 0. So now what this will be? Del T by del XT. So this will be del SR by RT. Let me see. This is the slope of this pressure. So, in a THCO2 diagram, THCO2 space, at constant pressure, the slope of the reaction is given by RT by del SR into N by X CO2 minus M by XH2. And we go into del P by del X CO2, and this is as constant temperature. So at constant temperature, this vanishes. Okay? And you can see that you will have RT by delta VR, RT by delta VR, this should be a negative sign here, and you can have NXCO2 minus M by XH2. This is what. So this PXCO2 is displayed on this diagram, PXCO2. So what you're trying to find out at a particular temperature, so you cut a surface parallel to PXCO2, cut your surface parallel to PXCO2, T is fixed. So you can see what you will have is minus RT by del AVR is equal to N by XCO2 minus XH2. You can remove the negative sign and reverse it. It will be the same. In the book, you will see it is reversed in the sense. But essentially, you have a minus sign here, which is not present in this part. Because here you have del XCO2 by del T. So here there is a term minus del SR. Now, when we talk of progressive metamorphism, normally we talk about increasing temperature rather than increasing pressure. It's increasing both pressure and temperature. But when we talk of increasing metamorphic grade, increasing metamorphic temperature, we have in mind an increasing metamorphic temperature. So what we are important for us is this diagram here. This is important for us. What we are looking at is this. Del T by del XCO2. How does temperature and XCO2 varies at constant pressure? And this is our equation for progressive metamorphism. You could also do it for changing pressure. You can also do it for changing pressure. You can also do it where XCO2 is constant and you look at the Clausius-Clapeyron slopes. That is normally what we do is we normally have a temperature pressure diagram and draw a reaction. Remember, this reaction that you're drawing is essentially an intersection of the curvature on the pressure temperature diagram. This is important. That this line that you're drawing is essentially the intersection of this reaction surface on the pressure temperature surface. These are intersections of two surfaces. Here, if we write doing like this, then XCO2 is constant. Remember one. Normally, XCO2 or XH2 is equal to constant. So now, we start looking at the slopes of the reaction. So I will erase this part. And I will write del T by del XCO2 at constant pressure is equal to RT by del SR into XCO2 minus M by, sorry, this was XH2O. XH2O, that's what it was. Now you see here, if we are trying to find out this, let us give these numbers. This type is 1, 2, 3, 4, and 5. Let's say there are 5 cases. You can say, sir, you can have n less than 0, n less than 0. Yes, you can have. So there will be another 6. Now in this you will see, these two are of similar types. 4 and 5 are of similar types, where H2O and CO2 are in both ends of the reactions. Again, this and this are of similar types. Why? You see, it has one of the fluid species, but the other fluid species is not there. But here, You have CO2 but no H2O. You have H2O but no CO2. Here you have H2O and CO2 both on the positive side, and you can have a situation 6 where you will have M, I will write it down, M less than 0, N less than 0. M less than 0, N less than 0. So that will be where both fluids occur on the same side of the reaction. So you can have both fluids occurring, fluid components occurring in the same side of the reaction. You can have one of the fluid components, this one, and you can have two fluid components in either side of the reaction. You can have all these three combinations, gives you 6 cases to deal with. Let's say we start with case number 1. Let's say we start with case number 1. We wrote a reaction recently, and what we are studying? We are studying, I will, CO2, okay. This is the situation. We are studying this reaction. What we are studying? We are studying the slope of the reaction in THCO2 space at P is equal to constant or derivative of P is equal to 0. This is what we are studying. This is what we are studying. Now let's say for example, now listen to this, it's very logical. At XCO2 is equal to 0. At XCO2 is equal to 0. What is happening? XCO2 is equal to 0 means this term, N by XCO2, is infinity. At XCO2 is equal to 0, or close to, very close to 0, this term is infinity. And this term, of course, is very small, M by XH2. So, the whole term is positive, and this term is always positive. This is always positive. This is always positive. So, what happens is, if you have NXCO2 and your XCO2 is close to 0, then this term is infinity. And infinity with a positive slope. Infinity with a positive slope. So, what happens? If it's infinity and a positive slope, it's like this, the slope of the reaction. At XCO2 is 0, it's infinity, tan theta 90 degree, and the slope is positive. Right? So here, at XCO2 is equal to 0, the result is positive infinite slope. Let's say what happens at XCO2 equal to 1. We are in this end. We are in this end. So what happens if XCO2 is 1, XH2 is 0? So if XH2 is 0, this term is infinity, but negative infinity. Negative infinity. So what happens? This will yield a slope which is negative infinite slope. Negative infinite slope. So you will have a situation where your reaction should be like this. So you can gather I will ask you so obviously what will happen is these two reactions will join and you will have a situation like this, where at this point, the slope is 0. The slope is 0, where you have A here, B plus MH2O plus NCO2. A, B plus MH2O plus NCO2. If you do the reaction, then they need to join in this way so that there will be a point of inflection here and the value for that should be a characteristic. The value for that should be a characteristic. So now you see here, if I take the slope here, horizontal line, take the slope, then this should be 0. So I can write 0 is equal to RT by del SR into XCO2 minus M by XH2. Which leads us to the fact that N by XCO2 is equal to M by XH2. Because RT by del SR is not 0. So NXCO2 by MXH2, this should be equal to 0. That means N by XCO2 should be equal to M by XCO2. Or you can write M divided by N. M divided by N is equal to XH2O by XCO2. Do you understand? So we have M by XCO2 is equal to M by XH2O. So M divided by N is equal to XH2O by XCO2. Remember, this is XCO2. Have you understood? So, if you have a reaction where XCO2 or M is to N is, say for example, M is to N is equal to 1 by 1, then your curve will be here. This is XCO2 equal to 0.5. If M by N is equal to 1 by 1, that means XH2O is equal to XCO2. That means XH2O equal to XCO2 is equal to 0.5. So you will have a graph which is symmetric around XCO2 is 0.5. But say for example, if you have a value, you see here XCO2 is higher here, XCO2 is lower here. So depending on the M by N ratio, your graph will be like this. Do you understand? Depending upon the M is to N ratio, your position of inflection at slope is 0 will occur at different points, and that will depend on M is to N ratio. So if your M by N ratio is 0.9 is to 1, 9 is to 1, then the graph will be here. Why? Because M is 0.9, N is 0.1 or 9 and 1, it does not matter. So the peak of the graph should be here. So that is very important to realize. This is very, very important to realize. That given the slope, this is important. You know, for a maxima or for a minima, the first derivative should be equal to 0. For a maxima or a minima, the first derivative should be equal to 0. So for a maxima or a minima, here it is a maxima, del T by del XCO2, this value needs to be 0. If this is 0, then this is what will happen. You will have an inflection curve here, and from which you can derive its M by N is equal to XH2O by CO2. So depending upon the stoichiometry of the reaction, M is to N ratio, the curve can be here, 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 and here, anywhere where the inflection point is. And that is important. I will stop here now. We will continue on this discussion in next lecture. Thank you.